In this video I'm going to show how to run a ZX80 ROM on my homemade Z80 computer. What I'll do first of all is I'll go through a demonstration of it actually working, and then I'll go through the source code and show how I got it actually up and running on this computer. So first of all I need to start off my terminal in my terminal session. So I've made my own terminal software, which I'll go through in a different video and explain why I've done that. So I start that there, and then I can start up my machine. I go through the bootloader process, and I get my menu up on the display in the terminal. And so option F2 is to run the ZX80 ROM, and there it comes up, and you've got a command prompt down the bottom. So if I just type in a quick program, 10, and I forgot that on the ZX80 you have to, some of the keywords you have to type in. So character string you actually have to type in. It requires brackets around the A as well, which it doesn't on the ZX81. I forgot to put the for loop in, so I'll start on line 1. So there's my quick program, which should show the character set off of the ZX80, and there it runs, and it finishes okay, and the error 020 to show that it's completed successfully at the bottom of the screen. If I hit enter, it goes back to the listing, and you can move the cursor around the screen up and down in the listing as you can on the ZX80, and edit lines. So that's the ZX80 ROM running on my Z80 computer. So in order to make the explanation of how the actual software works on my Z80 computer, I'm going to just go through the differences between the hardware of the ZX80 and my own Z80 computer. So in the memory map, the ZX80 computer has a 4K of ROM, which is its basic interpreter at the top of the memory. And then there's a big gap where it doesn't have any memory. And the default ZX80 you buy from the shop comes with 1K of RAM as standard. Then there's a big area where if you put in a 16K RAM pack, it would place it around this area in the middle here. And then at the bottom of memory, or near the bottom of memory, or I should say top of memory, sorry, is a mirror of the 1K of memory where it stores information about that needs to be displayed, and the hardware accesses this mirror, and it updates the display from the information it finds in this mirror of memory. So on my computer I've got a full 64K of RAM, which I can do what I want with. Now, first thing my software needs to do is copy the ZX80 ROM into the top of my RAM memory, because all the addresses in the ZX80 ROM are referenced from address 0, so it needs to run from the top of memory. In the middle of memory, because I've got full 64K, the ZX80, when it boots up, will find the full 16K that it can use for basic RAM, and it will actually use that and allocate it when it actually starts up, so I won't have to worry about that. But where the mirror would be of the 1K on the standard ZX81, I don't have to worry about that, because I'm going to disable interrupts, so nothing in the software is going to be accessing that memory, and I haven't got the hardware which accesses that memory, so I can ignore it. What I will do, as well as disable interrupts, what I need to do is insert my own display driver so that I can actually update the display on the terminal session. So that's how that will work. And if I go to the I/O ports, so in the I/O ports you've got 256 I/O ports on the Z80 microprocessor, and in the ZX80 it only uses a couple of them, so FD, and it uses that for a display sync, and as part of a cassette interface as well for reading or writing to cassettes. And the other port it has is a keyboard port, and again it uses that as a cassette interface as well for, I think that one's for loading and the other one's for saving. So there's only 2 ports to worry about, and in my Z80 computer all my ports for my CTC, SIO and PIO are around the E to EB port number range, which don't clash at all with the ZX80, so I won't have to worry about any of that. But I won't have to worry anyway, because any reference to the ZX80 ports, I'm going to have to patch the ZX80 ROM in order to insert my own software drivers to read the keyboard from the terminal and actually interpret that like it's the ZX80 key presses. So that's what's you should see when we go through the source code. So when my computer boots up, it comes up with that boot menu you saw. And when you press F2, it runs this code. And this code is what's responsible for getting the ZX80 ROM running and then keeping it running on my computer. And so the first thing it does is it copies itself into upper memory. So this 9000 address here, that's where it's going to relocate itself to. So if I just scroll down, this piece of code runs in lower memory and it copies this source code up into upper memory. And then it jumps to itself in where it's copied itself to in upper memory. So now it's running in upper memory. And then the first thing it does when it's there is it copies the ZX80 ROM into lower memory to the bottom of memory where it would be running on the ZX80. So now it's in a place where it can be running from. And then once it's copied the ZX80 ROM into the bottom of memory, it has to patch it a bit. So my computer has to do what the ZX80 expects it to do, but it mustn't do anything the ZX80 doesn't expect it to do. So the first thing is it sets up the interrupt mode. So the Z80 processor has 3 interrupt modes, and the ZX80 usually runs in IM1, which every time there's an interrupt, it goes to address 38 in memory, and that is where it handles updating the display normally. So I don't want it to do that. So my peripherals, which are going to be receiving characters from the terminal and then sending characters back to the terminal, operate in interrupt mode 2. So I have to, wherever it is in memory, which is this address in the ZX80 ROM, I need to replace the change to interrupt mode 1 into what I want, which is change to interrupt mode 2. Now my peripherals can receive and send characters over the serial terminal, but it also has a bonus effect of disabling the hardware interrupts that would normally update the display of the ZX80. So that's a nice easy win for that. And then the next thing I need to do, so this is where interrupt 38 is, and so I'm not expecting it to actually cause any of these interrupts because I've changed the interrupt mode. However, then it's always possible that somewhere in the ZX80 ROM it might manually try and call the interrupt itself. So I want to try and protect myself from that. So even though I'm pretty sure these will never get called, I'm putting in a little bit of safety. If the interrupt 38 happens, then I want to do something which hopefully gets it back and returns, which is this C9 opcode. It will return to whatever called it without actually having done anything. So that's just like a safety precaution. And then I need to insert my display driver where it would normally actually update the ZX80 display. So where there's an enable interrupts command, I have to replace it with this is a call to, and this is my assembly language routine, which will actually handle updating the ZX80 display, but on my terminal rather than displaying it in on an actual CRT display. So that's patched my display driver in, and then I have to do the same for the keyboard. But before I do that, so I'm in interrupt mode 2. So interrupt mode 2, whenever there's an interrupt, the interrupting device provides the lower byte of an interrupt vector. So I've got a Z80 CTC, Z80 SIO, and Z80 PIO. So each of those can provide its own interrupt vector. So whenever I get an interrupt, I don't have to work out what's interrupted me, because I know from the vector that's been provided, I can jump to an appropriate location. So I need to just, where I find this in the ZX80 ROM, I just need to update it so that it loads I, which is the upper byte of the interrupt vector, with my upper address of the interrupt vector. So then it will automatically continue to call my interrupt, which is what I need. And the final bits of patching is just to do with the keyboard. So wherever I get an in a C and it's to do with the keyboard port, I just need to call my appropriate handling routines. So this one is matrix detect, and then the next one is a matrix key press. So So these are three different areas in the ZX80 ROM, which I need to update the addresses, and this is just putting my own drivers in place, and then whenever someone presses the break key in BASIC, I need to also handle that. So I got the code running originally, but I didn't realize that there was another area to actually handle break keys, so it wasn't breaking into BASIC programs until I put this last one in, and then I could type in stuff and also break into BASIC programs. So, and I believe that's everything that needs to be patched. I haven't found anything else. It's always possible there's something else that might need to be patched, but it seems to run okay. And then after that's patched, it's ready to run the ROM. So if I go RST, which is just an easy way of saying jump to address 0, it starts executing the ZX80 ROM and it runs. But I need below is the places where it actually calls my drivers. So there's a matrix detect, which happens when someone presses a key, and it gets. So this is a character received from my serial port, and it has to decide how to translate it into an IO input from a ZX80 port, and that'd be easier to explain in the lookup table below. But all this code does is look up in a lookup table translation from an ASCII character press to an actual ZX80 key press event. And then there's another key code which does the same thing here. So this is the matrix lookup at the bottom, and then it just returns to the input instruction in the Z80 the appropriate value, and then here's the break key press, and again it looks up at the matrix keyboard below. So I'll just quickly skip to that across the display thing and come back to the display thing. So the actual lookup table is further down here, so just up a bit. So here's the matrix lookup, and this is a set of ASCII keys, so in the lowercase and then shifted, so in the uppercase as well, so you can see uppercase and lowercase c, uppercase and lowercase f. So all it does is it finds in this table when someone's pressed a key, like say someone pressed lowercase e, and then it can count across from the left 1, 2 and 3, so bit 3, and then from the top 1, 2 and 3, so it then places those bits onto the input instruction which requested the key press, and then the ZX80 knows which key press was actually pressed. And the display happens in a similar kind of way. So here's the display code. Now, in the hardware of the ZX80, it actually looks in the upper memory mirrored area, which is C000, but I don't have that. I don't have an upper memory mirrored, so I look in the lower memory where it's mirroring from, which is around this 4000 memory area, and wherever it finds one of these instructions, which is a 0x76, that means new line on the display. So it scans through this area of memory and it finds 24 of these, because there's 24 lines, and everything in between of these 76 characters is a character which needs to be displayed. So that's what it needs to do, is it just needs to loop through that piece of memory and display whatever character it finds. But there's one complexity to this, is that the ZX80 ROM, it doesn't use the ASCII character set, it uses its own character set. So you have to look up in the table a conversion from ASCII to the ZX80 character, and then you can return from, or you can put onto the terminal display characters which are converted from ZX80 characters into ASCII characters. So if I scroll down to the lookup table at the bottom, which you briefly saw earlier, so here's the lookup table for that. So these characters, as you see them here, are the ZX80 character set. So when it finds one on the display and it looks up, say there, it converts it into ASCII by saying on the right hand side here it's a 2 and then it's 6, so 26 hex it would convert that into, and then display it. So it goes through the whole display, converting the ZX80 character set into the ASCII character set, and then outputs it onto my terminal display. And that's all there is to actually getting a ZX80 ROM running on a Z80 computer.